This video is going to review alternating current. Everything we've done so far in circuits has been based on a source of EMF that produces direct current. Well, here in this image, on your page there, you have an example of a source of EMF that produces alternating current. What this means is that we have some external energy source connected to a coil that's going to be rotated in a magnetic field. That rotating coil through that magnetic field is going to cause a change in flux per change in time, and because of that we're going to have an EMF. Now that changing magnetic flux actually causes a changing EMF. How do we know this? Well, if we look at the equation for flux, all right, it's just equal to B times A times cos theta. As we vary theta over time, which is what we're doing in here, okay, we'll be also varying our EMF. In fact, a little calculus note, the EMF is going to be equal to n times the derivative, negative n times the derivative, the time derivative of the flux. If this is the equation for the flux, we see that EMF is just equal to n V A sine theta. Okay? So we see that both change. The coil is attached to a couple of brushes, all right, which basically those brushes maintain contact on a couple of rings, or it could be the other way around. Those rings are attached to the coil itself while the brushes are connected to the circuit. I believe that's what the image has here. Okay? And what that does is it maintains contact in the circuit, all right, without things getting tangled up. Okay? So there's always this conducting pathway, all right, in the circuit. So what we end up with is an alternating EMF, and that alternating EMF, of course, causes that alternating current. So when the coil turns within this magnetic field, we're going to do some examples of this in class as well. All right? What we have in this position, all right, is the plane of the coil is parallel to the field lines. All right? And the normal of the coil is perpendicular to the field lines. What this means is that theta is equal to 90, and for that makes phi a minimum, or 0. Okay? So in this position, based on the previous slide where I talked about the EMF being the derivative of flux, also times the number of coils, all right, what we end up with is the EMF and the current are at a maximum. In this second position here, the normal of the coil is going to be parallel to the field lines. So we have theta from our flux equation equal to 0 degrees, and therefore our flux is at a maximum. And when our flux is at a maximum, right, that's going to mean that our EMF and therefore our current are at a minimum. So, like I said before, EMF and current are directly related, such that the EMF is just equal to the current times resistance. And if the resistance is constant, we're going to have a similar looking graph for the current here over time. When we look at the EMF versus time and we change the frequency of rotation, if we double the frequency of rotation, that's the same thing as having the delta t. When you have the delta t, okay, for the change in flux, which is basically what's going to be measured by this frequency of rotation, you'd be doubling the amplitude of the EMF, okay? Right? You're decreasing the time interval over which that is changing. When you have the frequency of rotation, you're increasing the time interval over which this rotation is occurring. And when you increase that time interval, the change in flux takes longer, all right? And therefore you have a lower value for your EMF. That makes sense, all right? It's moving slower, there's less energy being put into it that way. So, alternating current, we get this nice little sine function, all right, detailing our EMF and our current over time. V naught is the peak or maximum voltage. You see that on the graph here, all right?
we're going to refer to it as this. So those of you who thought you were finished with sine and cosine from trig, nope, we love to use it here in physics as well. So the function of the voltage is just going to be equal to, all right, V naught times sine omega t. All right, this omega, just to remind you, is equal to the angular frequency 2 times pi times f. Just tells us how far through the cycle we have gone. All right, it's kind of like the phase there when we multiply it by the time, that is. Okay, we'll do some practice with this, and we'll keep coming back to visit it. So, like I said before, guys, current is just equal to voltage divided by the resistance. So for that, we just get V naught times sine omega t all over r. All right, and this is just the same as I naught times sine omega t. Remember, I naught is also referred to as the peak or max current. The power output of an AC generator, okay, is going to be given as before, where power is just equal to current times voltage. What you see when you do that, okay, is we get this I naught times sine omega t times V naught times sine omega t, and we get I naught times V naught times sine squared omega t. All right? So what we see is that the power is just equal to the max power, P max or P naught, whatever you want to call it, times sine squared omega t. So what this means is that there are no negative values here, right, for the power output. We see that the average power, all right, is just going to be the half the maximum power. This has some pretty big implications for the way that we discuss our current voltage. It's easy to see here, half the maximum power is the average power, but what about half the maximum voltage? What is that? Well, pardon me, not half the maximum voltage, I'll take that back, excuse me. The average voltage based on the sine curve. Well, if you look at this sine curve, the average voltage is 0. And the same issue happens for the current. Well, that's not acceptable when we're trying to do calculations with our circuits. So what we have here is a different way of analyzing it in terms of power. So P max is just equal to I naught times V naught. All right, so P max is just 2 times the average power. And so in this case, the average power is equal to 1/2 the maximum power, which is I naught times V naught. And we can actually split this up with I naught divided by the square root of 2 times V naught divided by the square root of 2. And we have these 2 new terms. These 2 new terms are called the root mean square of current, or the current, the root mean square of the current, all right, and the root mean square of the voltage. What this is, what we've done here, all right, is we have found, all right, a value that's the same as if the direct current at this value, all right, or voltage, all right, we're dissipating that power in a similar resistor, okay? This RMS value, all right, gives us that amount based on the power that's being dissipated in the circuit. So we will be using these instead of average current and average voltage because both of those would simply be equal to 0. Again, this is based on the fact that these values, these root mean square values, are the same values that we would get if we were analyzing a direct current circuit using that same amount of power. Another way to look at this is if you have V versus T. We have a little sine curve here. Let's see here. All right. So if we squared V, right, V naught squared times sine squared omega t is what that would look like. The whole function would be moved up, right, out of the fourth quadrant, and it would look something like this. Okay? If we took the average here, right, v squared divided by 2, right, and solve for v, what we would end up with, right, is this term, v all over the square root of 2. And this is what our root mean square comes from. All right. So in the US, most household voltages are rated at 120 volts at 60 hertz. When we say the rating, this is the RMS voltage. That's what the rating means right there. So V RMS equals 120 volts. V naught would just be equal to the 120 volts times the square root of 2. So the maximum voltage that we would be getting here is 170 volts. All right. In Europe, now we're looking at this voltage rating, 230 volts. So V RMS is equal to 230. And if we solve for the peak voltage from that sine curve, it's just going to be square root of 2 times 230 volts. And that's approximately 330 volts. Okay. So again, we can get the resistance here, all right, as long as we're just dealing with the consistent values, whether it's maximum or RMS values. One more time. All right, there's two ways to think of RMS. One is to square the function and then take the average and then solve for the value of the voltage of the current, and you're going to end up with V or I divided by the square root of 2 when you average it that way. Or to look at it as it's the same thing as if we were considering the power consumption for a DC circuit. So again, just to repeat that one, the RMS values are given as AC values to be used in calculations as if they were DC values. So let's look at this example. Again, treating things as if they're DC values. We have a stereo receiver that applies an RMS AC voltage of 34 volts to a speaker. The speaker behaves approximately as if it had a resistance of 8 ohms. Okay, so calculate the maximum voltage. It should be 34 volts times the square root of 2 is going to give us approximately 48 volts. All right, the RMS current, which is just going to be VRMS divided by the resistance, gives us approximately 4.3 amps. And the average power for this circuit, which is when we find the average power, it's just VRMS times the current. And that's equal to approximately 150 watts. We have a couple more examples to go here. This video is going to be a bit long. It's all right. So we have a 100-watt light bulb is designed to operate from 120 volts from alternating current main supply. Determine the maximum power of the light bulb. Well, P max is equal to 2 times P average, which in this case is 200 watts. The maximum current that is going to be drawn, all right, by the bulb. Well, there's a couple different ways we can go about this, but if we just look at P average, all right, is equal to the RMS current times the RMS voltage, and another way of writing both of those is just the maximum current divided by square root of 2 times maximum voltage divided by square root of 2. All right, we got the maximum voltage, or pardon me, the RMS voltage 120, so we can solve for I naught, all right, which is just going to be the square root of 2 times the average power divided by RMS. When you do that, you get approximately 1.2 amps. All right. For number 3, you got a maximum alternating voltage of 170 volts. It's applied across a 50 ohm resistor. Determine the maximum current. Well, again, as long as we stick with the maximum terms here, 170 volts divided by 50 ohms will give us the max current, and that's approximately 3.4 amps. Actually, no rounding there. And the average power dissipated by the resistor, all right, again, max current times maximum voltage, all right, divided by 2 can give us this value. So P average, just maximum power divided by 2, or in this case, I naught times V naught. That's 289 watts. Yes, rounding we really need to be sig figs, right? So 300 watts. And with this other one here, yeah, once again, that's all right. Anyways, so again, the point is, look at the equations and look at the graphs and make sense of the graphs. RMS is just another way of communicating a value that otherwise would be 0 if we took it as the average of the sine curve that we'd be considering. So we need an actual value that we can work with. And it turns out that this, because of power, all right, because of the power dissipated in circuits, the root mean square value actually holds physical significance. So check the math, check the physical relationships there from when you learn circuits, and read the textbook on this, all right?